So in this lecture, we are going to we're going to discuss measurement of high voltage. Once we have generated the requisite high voltage and we have the experimental setup in place, we need to measure what are the voltages that we are applying across our insulation. If we are doing disruptive voltage test, at what voltage does the breakdown occur? So therefore, we need to be also measure the high voltages that we are working with. Apart from the basics of measurements of high voltages, there are many other diagnostic tests that insulation engineering involves, but that we are going to discuss in a later lecture. Right now, we will only talk about the basics of measuring high voltages. So when you talk about measurement of high voltages, we have to consider that there are various kinds of voltages that we work with. In case of DC, we are interested in the mean voltage. In case of DC, with a high ripple factor, or especially in case of AC, we are more interested in the RMS value rather than the mean value. And given that high voltage engineering involves a lot of extreme voltage values, involves a breakdown at the extreme values, the peak values, we are often not interested in the RMS quantities, but rather more interested in the peak values where various phenomena would occur. So for DC, AC, as well as impulse voltages, we are interested in the measurement of peak voltages. Sometimes, especially in case of impulses, we are also interested in the voltage shape, because when we perform the tests, we need to make sure that we have the standard shape of the wave, that voltage wave that is being imposed, the shape that is governed by the IEC recommendations, like 1.2 / 50 microseconds for impulse, 250 to 500 microseconds for switching. So this kind of wave shapes we are also interested in. When we talk about measurement of peak voltages, the first thing that comes to mind is the sphere gap. The whole principle of the sphere gap is that if you have two spheres facing each other, so two spherical electrodes, which are separated by a small distance, when I say small distance, what I mean is that the distance of separation should be small with respect to the radii of the spheres, because that would ensure that in the gap distance, we would have a uniform field. If the gap distance was much larger or comparable to the radii, this condition would not be fulfilled. The advantage of sphere gap is that, firstly, there is a considerable region where you have a perfectly uniform field, and whatever uniformity or non-fringing there is would occur away from firstly, the non-uniformity is much less than, let's say, when you have a parallel plate, a finite parallel plate, which ends in sharp edges, or even a rod. You have much less fringing even at the edges, and because you don't have any edges, but you have some fringing outside the region where the spheres are closest. But then the fringing takes place, the non-uniformity or field enhancement takes place in a region which is away from the smallest gap distance, and therefore breakdown, even with small non-uniformities in that region, breakdown is not likely. Breakdown continues to be likelier in the uniform field region. Also, so therefore the spherical sphere, of course, it gives you the peak voltage, because at a particular setting of the spheres, breakdown will happen as soon as the peak voltage is reached for whatever short time. Advantage of the sphere gap is it is simple, it's easy to use, it is not prone to electromagnetic disturbance, but we need to calibrate it. That is, for a particular setting, we need to obtain the voltages at which the sphere gap breaks down. And only when we have a calibration table, we will be able to use the sphere gap arrangement to measure voltages, in the sense that you apply a voltage, and when breakdown occurs, you know what the voltage must be for that setting and for that radii. And these specifications are given by the IEC recommendations. For every sphere, for every spherical diameter, the sparking voltage is a nonlinear function of the gap distance, because as you go further and further uh, uh, further and further away, as the gap distance increases for a given radii, the field inhomogeneity increases. So you're not working with the same Schweiger factor for the field, and therefore just increasing the distance will not increase the voltage of breakdown voltage linearly. It will be a nonlinear measurement, and this is pretty explicable from the physics of breakdown. How do we use this sphere gap for measurement? First thing that we need to do is we have to establish a relation between the high voltage. So as measured by the sphere gap, what we mean by measurement of the sphere gap is positioned at a certain gap distance, gap separation, and then you apply a voltage and the sphere gap breaks down. At this voltage, there has to be a relation between the high voltage as it is measured by the sphere gap in some manner, and this will be indicated either by a voltmeter or an oscilloscope or some other device which is connected in the control circuit of the equipment. So there has to be a control circuit or a measuring circuit which takes inputs from the applied voltage at which breakdown occurs and reads the breakdown voltage. This relation, however, will cease to be valid if the circuit is altered in any respect other than a slight change of spacing. A slight change of spacing means we maintain the same Schweiger factor with respect to the radii and the distance. So when the radii tend to get to the same order of magnitude as the distance, this will no longer hold. And if you change anything in the external circuit or the control or measuring circuit, then this condition will not hold. So therefore, we have to, after we have established we have set up the experimental setup, we need to calibrate the circuit and proceed with the measurements. Remember, if there is dust or fibrous material in air, there might be erratic, disruptive discharges. These will be random and stochastic in nature, so you really cannot control. You can always try and work with spherical surfaces which are as clean as possible. They're polished, no protuberances, the air is clean. All that is there, but there might still be certain factors which will cause random breakdown at voltages lower than expected. And therefore, it may be necessary to carry out a large number of tests before consistent results are obtained, and we would need to perform censoring of experiments. So when we know that definitely some extraneous factor, some random factor is causing the breakdown, and it is not just dictated by the gap spacing, we have to censor those readings. We actually follow different procedures for measurement of the different kinds of voltages. For DC and AC, we apply a voltage which has a magnitude which is low enough not to cause disruptive discharge during the switching transient. So there might, when you're raising the voltage, there might be some transients because of the circuit, because of the equipment. Those transient values will also increase in peak as you apply higher and higher voltages. So when you apply the voltage, you have to be careful that transients do not cause breakdown, because then you will not be able to perform the experiment. After you switch on without failure, you raise the voltage sufficiently slowly so that you can, at the low voltage indicator, where you have an indication of the voltage in the across the sphere gap while it has not broken down. So you have some kind of arrangement which converts the voltage across the sphere to a low voltage value, which can be read at the operator level for safety, for operational safety. So you have to give that time. So you need to raise the voltage sufficiently slowly. And at the instant of disruptive discharge of the gap, this voltage will be available in the meter. Alternatively, a constant voltage may be applied across the gap, and the spacing between the spheres may be slowly reduced. So you apply a voltage and initially nothing happens, and then you slowly keep reducing the gap distance and allow disruptive voltage to occur. So in this way, the breakdown will not be caused by transients. That is the advantage over the previous method. There are also motorized sphere gaps where you control the gap distance using a motor. So therefore, you have very fine control over the gap distance. For impulse voltages, however, the procedure is quite different. The spacing of the sphere gap or the charging voltage of the impulse generator is adjusted in steps, and these steps should not be more than 2% of the expected disruptive discharge value. At each step, you need to make 6 applications, and between successive applications, there should be at least a 5-second interval. And when you work at a particular step, the value which gives 50% probability of disruptive discharge is preferably obtained by interpolation between at least 2 gap or voltage settings. So let us say 2 gap or voltage settings, one resulting in 2 disruptive discharges or less and the other in 4 disruptive discharges or more. Because this is a statistical phenomena, you may not be in a position where you have out of 6, there will be 30% breakdown. So you work at 2 voltages, you identify 2 voltages. Let us say at the lower voltage, you have only 2 disruptive discharges or even less, at most 2 disruptive discharges. So that means out of 6, you can have at most 2 disruptive discharges, you can have less. Identify that voltage. Now keep on increasing the voltage and identify the next voltage where you definitely have 4 discharges or more. So 4 breakdowns or more. So at least 4 breakdowns. So mark these 2 values. V1 where you have at most 2 discharges, V2 where you have at least 4 discharges, and by interpolation between these voltage values, you can obtain the disruptive discharge voltage where you can expect 50% probability of failure. Now, the breakdown of the sphere gap also depends upon the reference conditions, the atmospheric conditions. So therefore, once we have read out this voltage from the measuring equipment, we will have to add some correction factors. So if VD naught is the voltage which is obtained from the meter reading, then VT would be the disruptive voltage at that atmospheric conditions. VD is equal to KD into VD0. KD is a correction factor. The correction factor is also dependent upon the air density, relative air density, RAD. What is our relative air density? The relative air density, RAD or delta, is defined as the ratio of P by P naught, the pressures, the atmospheric pressures, and the temperatures in Kelvin. So P by P naught into T naught by T, where T is 273 plus T. So this is the relative air density. P and T, the test condition ones, and P naught and T naught, the room temperature or standard pressure and temperature. From this, you obtained RAD, and then you use the RAD to obtain the correction factor KD. So, for example, if you have a relative air density of 0.85, the correction factor is 0.86. So, if you measure 10 kV breakdown, the real breakdown voltage would be 0.86 into 10, which is 8.6 kV. So it's actually lower. In this discussion, the influence of humidity is neglected, but if you are working with humid conditions, which are way off normal humidity conditions, the influence of humidity also has to be taken into account and the correction factor incorporated for humidity. Just as we use sphere gaps, rod gaps may also be used with proper calibration. Rod gaps are not as dependable as sphere gaps, but with proper machining, they can be used. Next, we come to electrostatic voltmeters. Electrostatic voltmeters are a very common class of voltmeters for measuring the voltage, where we have, let's say, 2 plain disc electrodes, and when we apply a voltage V between the plain disc electrodes, a field F is produced. Because of the field F, there would be an attractive force F on any area A of the electrode. This F is given by minus dW dx, where W is the electrostatic energy. So the magnitude of F for parallel discs can be given as epsilon A E square by 2 if you have a uniform field, because these are plain electrodes. And this can be written as epsilon A by 2s square into V square. So therefore, the attractive force is directly proportional to the quadratic of the voltage across the electrodes, and it is also dependent on the area of the electrodes and the distance of separation. Now, if the voltage is time dependent, then if we integrate this force over the entire time period, what do we get? So let's take this force and integrate it over the entire time period t, 1 by capital T integration 0 to t ft dt. So this is the mean value is equal to epsilon a by 2s square 1 by t integration 0 to 2v square tau dt. And what is this? This is nothing but the RMS value. So therefore, the mean value of the force for a time varying force works out to be proportional to the root mean square of the voltage. So what is done is one of the electrodes are allowed to move, and when the movement is then transmitted and amplified, if there is any change in field due to the movement, that is neglected because these are very uniform field, so you only have a small change. The attractive force, remember, is always positive independent of the polarity of the voltage. So the polarity of the voltage has to be worked out, but the reading will be dependent. So if you have a deflection which is proportional to the mean force, this will be proportional to the root mean square RMS voltage across the electrostatic voltmeter. We also use ammeters or voltmeters where we have some mechanism to reduce the high voltages that we want to measure to measurable quantities. So if you want to measure a high voltage capital V, it is reduced to a small quantity I, either a small quantity I, a measurable current magnitude, or a measurable voltage magnitude. So that what you're measuring is a low voltage quantity which can be safely measured by the operator. So you have to first reduce the high voltages to measurable quantities, either adequate currents or low voltages, and then you put a microammeter in series with a resistor capital R of sufficiently high value so that the loading is small, the loading of the high voltage source is small, and you have a very small voltage, a small current I, and this current can be read off across a resistor. Or you can have a voltage divider like this where V2T is equal to the VT that is measured is given by V2T, which is the measured quantity, and the ratio of the measured quantity and the supply voltage or measured voltage. This is what is the reading voltage, and the measured voltage has a ratio of 1 plus R1 by R2. So the resistors R1 and R2 have to be appropriately chosen so that we can reduce the dangerous voltages to safe voltages that can be easily measured. Another class of dependable equipment are the generating voltmeters or field sensors. They also measure the RMS value. In this case, what you have is you have a spherical electrode, and then you have 3 electrodes. You have the actual electrode, which is marked by A. Around these two, you have a guard electrode, so you can imagine this to be a circular shape electrode surrounding the measurement electrode. So this is the guard electrode, and connected by a spring to the guard electrode is a movable electrode. Let's call it M. Now let us imagine that M is fixed, and you apply a voltage V here. Now as the voltage changes, because of that voltage, there will be an electric field here. And because of the flux lines cutting A, there will be some charge on A. Now remember, A is grounded. Now let us imagine that M is fixed and we change the voltage V. Now if you change the voltage V, the charge Q on this A will change. And because A is grounded, that small change in charge will result in a current I flowing from the electrode A to the ground. So this current, if it is integrated over the time period, then this is given as over the entire area is given as Q equal to I naught sigma dA, where sigma is the conductivity, charge density, where sigma is the charge density, which can be a function of time as well as the area. So if you have a larger area, you will have a larger charge density, and so therefore the total charge involved in the current that flows to ground from this electrode, Qt is equal to double integration A surface integral sigma Ta dA, which is equal to epsilon integration Eta dA. So therefore, this charge quantity or the current integration of the current quantity is a measure of the varying uh, field intensity in between the two electrodes. You may also have a situation where the voltage remains constant. If this is a constant voltage that we want to measure, we cause the movable electrode M to move slightly, so that the field configuration is not greatly changed. Now, if you move M comes a little over A, and therefore the flux cutting the plate A changes. So there is a change in the charge on the sensing electrode. If the flux lines do not cut A but are intercepted by M, they will not cause a charge on A. So there will be a change in the amount of charge charge Q on A, and that will again result in a current. So IT in this case will be equal to dQ dt is equal to ddt of integration sigma A dA, which is equal to epsilon ddt EA dA. IT is therefore equal to ddt CT/VT. So the current is a measure of the change in voltage or the capacitance. Generating voltage meters are preferred because they are linear instruments and they can be applied over a large range of voltages. Next, we come to the Chaff-Fortescue method. This is a method for measurement of peak voltages. We've already talked about measurement of peak voltages using sphere-sphere geometry, sphere-sphere electrodes. There are other techniques for measuring peak voltages also, but let us discuss the Chaff-Fortescue method. In this case, what you have is you have a standard capacitor connected across the voltage supply, and then this is the current flowing through the capacitor IC is branched into two branches by two diodes. This is forward bias, so this is reverse bias, and therefore you have this IC flowing through plus IC in this direction and again minus IC in this direction in two different half cycles. And in this circuit, in any of the branches, you use a current integrating ammeter. So the current integrating ammeter will be able to measure a current I, which is equal to 1 by T integration T1 to T2 ICT dt. T1 being the zero crossing, let's say, and the T2 is the next zero crossing. In that case, this can be written as C by T integration T1 to T2 dV, which is nothing but C by capital T, V plus max plus V minus max. So therefore, what you measure, I, is nothing but the capacitance C, which is a known capacitance, multiplied by the frequency into voltage peak to peak. In case of a sinusoidal wave, this will be 2V max. So therefore, using a current integrating ammeter, we are able to measure the voltage, peak voltage. Apart from that, voltage dividers may also be used. Either resistive dividers or capacitive dividers might be used for measurement of voltages. This is a very basic discussion on measurements. In a later week, we will discuss various other diagnostic methods, and mostly with more emphasis on non-destructive methods. We will discuss the various diagnostic techniques that are used for insulation diagnostics and analysis.